Factoring patterns. Today we are going with difference of two squares. So hopefully you're going to see some resemblance to when we are multiplying these things out, but we're working backwards. It's our whole goal here with all these things is working backwards. So here are the guidelines that we'll have when you're factoring the difference of two squares. First, there's only going to be two terms. Okay, so that kind of limits your choices in terms of all the different factoring patterns we have, which ones you want to look for. Only two terms. Next, the first term must be a perfect square. And that means that the coefficient is a perfect square, knowing your first 20 perfect squares. We've done bonus work on that. And the variables need to be perfect squares. It must be a subtraction problem. And the second term must be a perfect square. Hold on, I want to adjust this real quick. There we go. So as we look through these things, and that's coefficient and variables as well, how do you know when a coefficient, how do you know when a variable is a perfect square? Glad you asked. Perfect squares in terms of coefficients, you should know your first 20 perfect squares by now. The first 10, absolutely inside and out. But real, recognize them and do that. If not, have that list handy so you can see them. On the variable side, I know a variable is a perfect square if it has an even power. X squared, x times x, something times itself, x to the fourth. Now there's other things, but it's got to be times itself to be a perfect square. So it's x squared times x squared. Another example, x to the 10th. That is x to the 5th times x to the 5th. But now if I said x to the 7th power, not a perfect square because you're not multiplying something by itself. So let's see how these work in here on these. So you're being asked to factor the following polynomial. So in order to do so, we look at it. We know there's only two terms, so that limits all of our choices. I know it can't be grouping. I know it can't be any trinomial stuff. So it's either going to be a GCF or the difference of two squares. The only ones we have for two terms. So I look, a 4, a b squared, and a 21. There are no greatest common factors. So the next thing, is this a perfect square? I will think. What times itself is 4? All right, 2 is. What times itself is b squared? B is. So here's what I like to do. If it's a perfect square, I like to write the square root of it right there because I know I'm going to be using it. I know it's a subtraction problem, so good, that's going. Now is 121 a perfect square? I got to know my list. It in fact is. So it is 11. So now, I'm going to go step back here real quick. We did all this stuff. What does all this stuff factor into? The difference of two squares. So if I have a squared minus b squared, it's got to be difference, perfect squares, factors into a sum of the square roots times a difference of the square roots. And if you recall that shortcut when we did it, we said that the inners and outers of FOIL we didn't have to do, and we get to this answer. That's where that comes into play. So the difference of two squares will factor into what's called a sum, square root of a, square root of b, times a difference, square root of a, square root of b, in there. So it factors into a sum times a difference. That's our technical mathematical formula for you. So applying that here, let's see. We know that's a perfect square, check. We know that's a perfect square, and we know it's subtraction. So according to this, it's going to factor into the quantity of the square roots here and here. 2b plus 11 times 2b minus 11. You're done. There's going to be other things to do, but we got to have the factoring patterns down. There it is. Follows that pattern because all of these checks were yes. All right. Let's try this example, if you will. All right, let's look at this one. Here we have, we're being asked to factor. Again, two terms. Is there GCF? No, there's not. So we look, do we have perfect squares going on? Square root of 16, 4. Square root of h squared, h. So that checks. Square root of 9, 3. Good. Square root of a squared, a. That checks. Final check. Is it a subtraction problem? Why, yes, it is. So we factor it. This is the difference of two squares. So we will have the first one, 4h minus 3a times the quantity of 4h plus 3a. Use the square roots for the first term, here and here. Square root of the second term, here and here. A, sorry. Now somebody will say, well, wait, last one you had a plus sign here and a minus sign here, and now you switch around. Doesn't matter. The 16h squared, what makes that up, has to go first. The second term's square roots have to go second. All right, so now let's look at this one for a second. This one again, two terms. At quick glance, though, is it, or are they, I should say, perfect squares? That's an odd power. No, it's not. So is that. Matter of fact, the number 5, nothing times itself. 45, not perfect squares. So before you give up, you are now to the point where other factoring patterns might be piggybacking in here. And you have two of them to open, or use one to open up the door to the other one. So let's look for a second. Remember, it's only two terms. Trinomial, out the door. Grouping, out the door. It's either GCF or difference of two squares. We just said difference of two squares not going to work, but let's look. Is there a GCF? The correct answer is yes. You can get a 5x out of each one of these. So we factor it out. We don't get rid of it. It just goes on the outside. Now, what's this divided by 5x? That would be x to the 4th power. What's this divided by 5x? Minus 9. But before you stop, if, just like fractions, you might think you've got it reduced, but there's something else that can be done, always got to check. Does this fit a factoring pattern? Is this a perfect square? Yes, it is. Is this a perfect square? Yes, it is. And are we subtracting? Third answer, yes. So we continue our patterns. Now, our GCF, still there. Keep it. So we got 5x. Now, square root of that, x squared. Square root of that, 3. They fit all three checks, so we get a sum times the difference. X squared plus 3. X squared minus 3. So kind of the same rule. Never let a fraction go unreduced. We don't want these to go unreduced as well, or unfactored, if you will. All right, let's see what we got here in this next one. So we look, perfect square, check. Perfect square, subtraction, boom. We're in business, so let's get to work. Square root of this is b squared. Square root of that is 4. All right, so we'll have b squared plus 4, sum b squared minus 4. And again, start checking these things. You've now seen all these patterns. You're going to start seeing things step it up a notch in terms of expecting you to remember things. There is no sum of two perfect square factor patterns. That's nothing we can do. But examine this again. Perfect square and subtraction. You can keep going on this part of it. Square root of b squared is b. Square root of 4 is 2. So here's what we got. Somewhat different, but somewhat the same what was going on there. Multiple steps. Here, neither one of these were the difference of two perfect squares. Here, this one is. B squared plus 4 remains. And now we break this down into another sum and a difference. B plus 2 times the quantity of B minus 2. So don't be surprised if you see more and more of those as we work through.